suppose that must be my signal to start. Everything okay? Yep. Okay. Oh, slightly chopped off the top. Hi, I'm Mike Crowe, and welcome to my tale of modernising code, some of which is nearly 20 years old now. The techniques I described today changed about 7,000 lines automatically and safely, and hopefully will change a lot more in the future. Or, in other words, how you too can change about 7,000 lines of code automatically and safely. By the end of this talk, I hope to have given you an idea of some of the things you can do with clang-tidy. That's clang-tidy as it's released, but also how you can modify and extend clang-tidy to solve your own problems. And maybe get some of those changes accepted into the released clang-tidy for others to use and build upon themselves. Before I go on, thank you to my colleague Tim Morris for using his machine learning skills to generate this picture. Don't look too closely at it. What's going on with this lamp? It's actually falling off or something. I don't know. It's certainly more impressive than I could have drawn anyway. If you don't understand something I'm talking about, then tell me straight away. But if you have deeper questions, leave them to make a note of the slide number, bottom right-hand corner, and ask them at the end. So I've been programming in C++ for over 30 years now. But I'm not someone who really speaks standardese and stuff, or really knows about the intricacies of how to parse C++. I've also been working with embedded Linux for over 25 years, initially MP3 players at the top, and for the last 18 years on digital signage media players, a bright sign at the bottom there. So bright sign has a main application written in C++ that makes use of lots of C and C++ libraries on top of Linux on various different processors. Those libraries include libcurl and gstreamer and Qt or Qt, depending on how you want to pronounce it, Chromium, MPV, and proprietary code from chip vendors. The main application dates from about 2007, but it continues to make use of some old C and C++ code from older products as well. We have a dozen people working on Bright Sign OS itself, and many more work on cloud stuff and other client applications and things. Bright Sign's main C++ application used static instances of logging objects such as in each source file, looking remarkably like that. The code was a thin wrapper around printf, and it dates from the C++ 98 era. It certainly isn't perfect, but it's worked well enough for many years now. The use of the static there isn't particularly modern, but it is easy to write. It's all on one line. It makes it easy to enable or disable logging in a particular source file during development by just tweaking the declarations. There are other alternatives you can use, such as never log and always log. You wouldn't be surprised to find out. So, in order to implement this, we're going to provide a class that will always log and one that will never log. And we still need to use the preprocessor to distinguish between those two cases at compile time. This means that we can enable extra logging automatically in debug builds, and then that gets disabled in the release builds. Error log can be always log, and it comes out all the time. The implementation of never log is straightforward. The function call operator, bracket, just never does anything. Pretty boring. And the compiler can throw away the format string parameter as well because it knows it's not going to be used. The implementation of the function call operator in the always log case needs to actually do some work, so it's on the next slide. This could probably be done with a bit of if context for these days, but Jason isn't in the room, so I don't think. But I haven't tried to do so myself, but it probably could be. I'm not going to go into detail with this because it's not really important to this talk, but this is basically how you'd have written it 40 years ago in C. But here's a skeleton implementation. It uses C-style variable argument lists, which rely on knowing the types of each argument in order to extract them from the variable argument list at the end there. Printf uses the format string to determine those types. but in standard C or C++, there's no automatic checking of that format string. Although it is possible to get GCC and Clang at least. I haven't used the Microsoft compiler for a long time, but I can't believe it doesn't by now to do that checking. But there's more on that topic later. So you can see that depending on the value of the debug macro, the log statement will either emit no code at all, or it will emit code to invoke the function call operator on always log. Error will always emit code to invoke the function call operator, so the log messages come out or not. So all was fine, or mostly fine, for about a decade. We thought it would be nice if it were easier to log our own types more easily. We considered using a streams interface instead, but people didn't like the verbosity of streams, to be honest. They're a bit long-winded. That would have helped with the type safety, though, using streams, but we never got around to it. So up until 2017, all our products had been 32-bit. So on 32-bit Linux, a long is 32 bits, and an int6040 is of type long. So this requires you to use either %LD or %LLD, as I've used there, with printf or these log statements. So the code was full of using %LL to format int64t and uint6040. And on 64-bit Linux, a long is 64 bits. So int6040 is of type long. So that requires you to use just a single L. There's no single way to specify how to format that parameter B that's correct for both 32-bit and 64-bit Linux. If you think you can think of one, hang on a minute. To be honest, getting all the other format specifiers right is a bit of a pain too. Though, you know, those compiler warnings I talked about previously were really quite useful. Except in this case, where they actually hindered. Despite the warning at the bottom there, the right thing would actually happen at runtime, because a long is 64 bits in the same way on start again. A long is 64 bits on 32-bit architectures, and a long is 64-bit on 64-bit architectures. So the right thing would happen. You get a similar warning to that on a 32-bit Linux if you try to do the opposite. But those warnings were really useful in all the other cases to stop us provoking undefined behavior. There's one for your bingo card. That would lead to incorrect output or even crashes. So disabling those warnings wasn't really an option. So although I haven't programmed Windows for many years, I believe that int6040 is a long even on Windows, 64-bit Windows. So this kind of problem occurs if you're targeting a mixture of 64-bit Linux and Windows as well. So I lied when I said that there wasn't a way to specify how to format B. The C and C++ standard solution is a header called int-types.h. It provides macros that expand to the correct string. But they're horrible, absolutely horrible to type and read, as I hope you can see here, Exhibit A. Best avoided, unless you have no choice, in my opinion. They're just horrible. But I did find a better solution. The format C++ library had been on my radar for a while, and I realized it completely solved this problem. Its printf function uses templates and parameter packs at compile time rather than C variable argument lists at runtime. That means it can be much less picky about the exact type of the arguments. I could have just used %d or %u as appropriate everywhere there. It doesn't really care about the size of the type that's passed, although it does still require distinguishing between strings and integers. Unfortunately, there's no compile time format checking anymore. But it matters less since mostly you don't need to get them spot on right, and you don't get undefined behavior at runtime. You might get an exception, but you don't get undefined behavior. But to be honest, the format string has to be quite wrong. It's usually the number of arguments that are wrong, and that will give you an exception. So here's the new implementation of the operator overload, which now uses a parameter pack to format the arguments on. We need to be prepared for format fprintf to throw an exception if the format string is wrong. So we need to catch that. We decided we didn't want those exceptions to escape, because the fact you can turn tracing on and off means that we might accidentally have ones that are incorrect, and we didn't want those to just terminate the program or anything, or cause other error paths to be followed. And this has been a great solution for the last 6 years or more. So more information about that transition can be found in the ACCU Overload issue 145, which is available free on the ACCU website. Right. So having switched to the format library, the code was now full of unnecessary calls to the standard string cstra function. And people were just copying these into to new code, making it basically harder to read, and sufficiently long strings less efficient too. At least that's what I thought. But when I started writing this presentation, I thought I'd better go and check. And it turns out that removing the cstra call there generates 2 more instructions at the call site, but means that the implementation doesn't need to walk the string to find out how long it is at runtime. So, it's probably swings and roundabouts. It doesn't make a difference. So let's talk about it being more readable, shall we, rather than it being more performant. So this led me to my first foray into clang-tidy. So hopefully everyone here is aware of clang-tidy, but just in case, clang-tidy is a tool to perform automated checks on your code, many of which can apply automated fixes. Many of the checks can be customized, and clang-tidy is part of the LLVM compiler infrastructure project, along with the clang-C and C++ compiler itself. You don't need to compile your code with Clang, but your code does need to be able to be compiled with Clang to use clang-tidy. So we still use GCC to compile most of our code, including the code we're fixing here. But we needed to fix a few things that GCC was happy with, but Clang didn't like. And we had to tweak some of the warnings that we enable as well. So you can run clang-tidy on a single source file easily enough. By default, it enables a set of checks of its choosing, which you can then disable with the -*, and then enable the ones you want. So it will modify the original source file automatically if you pass the -fix option. If you don't, it'll just tell you about the things it would have fixed and other things that identifies wrong with the code. So this check here, coincidentally, is one of the refactorings from Jan's talk just before this one. It is replacing an old style for loop with a modern ranged for loop. Right. And that's the one we enabled specifically at the top. Rather than specifying the list of checks on the command line, you can create a .clang-tidy file in the current directory or in any parent directory. This is useful if you want to enable a lot of checks or set configuration options on those checks. And you can commit that to source control as well if you want to, and keep running it over and over again. Of course, in real projects, you'll have a lot of compiler options to specify to include you'll need to have a lot of compiler options to specify include paths for libraries and maybe some preprocessor defines and things. If you're using CMake, Mason, or probably various other build tools, they can generate a compile commands.json file. It contains all the compiler options for each source file individually. Ours is only about 7 megabytes. This is the same file that's used by the clang-D language server protocol server, which is used by VS Code and other editors for code completion and feedback. There is a tool called Bear or build-ear that wraps running whatever build system you're using and generates a compile commands.json file. I ended up modifying our make files to generate the compile commands.json file because all the information was there in the make files and it was straightforward enough. Clang-tidy just automatically uses the file if it can be found. Of course, you could tell clang-tidy to look at the files one at a time, but it'll be much faster if it can run in parallel. If any of the fixes that clang-tidy would apply are in header files, then there's a risk of racing against other invocations that are reading those files. You'd think that would be a problem solved in the tool itself, but apparently it isn't. Perhaps that's because clang-tidy comes with a Python script that runs the tool in parallel across all the files and then applies the fixes in a separate pass afterwards. It's a standalone script in the LLVM repository. Debian does install it as part of its clang-tidy package, and that's how we invoke clang-tidy. Clang-tidy can only fix code that would be seen by the compiler. If you use the preprocessor or build system features to have conditionally compiled code, then clang-tidy can't see it. So you need to run it with all possible build configurations. And even then, of course, it can't fix the code that's inside #0 or in comments. Clang-tidy checks are written using a large library of general-purpose abstract syntax tree, or AST, matchers that form a domain-specific language, or DSL. Those are used to generate specific matchers for the contracts to be tidied up. Clang-tidy already had a check that removed unnecessary calls to a standard string CSTR, and in fact, standard string data as well, because they're basically the same these days. And it was called readability redundant string CSTR. That's definitely readability again. I just needed to modify it. Unfortunately, it hasn't chopped the top off. I just needed to modify the clang-tidy code to add a matcher that would match calls to the always log operator, bracket function call operator. So that matcher can be built up out of smaller ones. This being C++, we're going to have to read it from the bottom upwards. Okay. I'm a bit further away from that than I was expecting. Is that okay if I wander over there? Okay, so we're looking for a C++ operator call, which has the name of bracket, so it's the function called invocation operator. Argument 0, which is the this pointer effectively, is either the always log class, which we'll come to later, or it's the never log class, which we'll come to later. And if we find that, for every argument which has a parameter which contains a string CSTR call expression, which we'll come to later, at that, to be honest, I'm not really sure exactly what that bit does, but it's necessary to make it work. I think it just means it doesn't really matter what the parameter is, as long as it matches that. Yeah, but as I said, I'm not an expert in this. So although we could have substituted that always log class expression into the matcher directly, it's clearer to separate it out to a separate variable. The never log class expression is exactly the same, except for the obvious difference. So it has canonical type, makes it see through type defs. So even if you were messing around with type defs, it would know that it was the right type. The string CSTR call expression matcher was already part of the code existing in clang-tidy, and I could just use it as it was. It creates kind of named bindings to certain parts of the AST so that it can be referred to easily when the check is actually run later to remove the CSTR and data calls. I didn't need to make any changes there. So, arg is the expression that the CSTR has been called on. Member is the member function call expression. It's used to differentiate between the pointer to member and the dot operator, because you need to deal with those slightly differently. And call is the entire expression being considered. So if it weren't for the pointer to member case, of course, you could just replace the text of the call by the text of arg, but because you might sometimes have to dereference it. So clang-tidy is mostly tested with lit tests, which check the tool emits the expected messages and applies the expected fix-ups when given certain input. They help make quite a rapid edit debug test cycle. It's a bit of a pain to decipher the output and work out what you've got wrong. So what we've got here is, so that's the statement we're expecting to get a result on, which we're testing basically. That says, I'm expecting to get this warning message mentioning the check name. So I'm going to get one for each of these arguments at columns 26 and 38. And then this is what I expect the fix to be when it's done. So the C calls have been removed. Yeah, in more than one case, I ended up creating a separate test file that could just contain the one test that I was debugging, because the output of the lit tool can get really quite confusing if you have lots and lots of them in the same file. And that's how you normally write them. So I now have my own custom version of clang-tidy that I could run against our code. It fixed 1,000 lines over about 200 files. It was only a one-off operation, so it didn't matter that I had to build clang-tidy myself to do it. As part of that, I also had to fix a bug in the existing check involving that operator arrow overload there. I thought my fix was a hack, because basically it was putting an extra arrow in, and I just deleted the extra arrow by removing it from the output, and they just accepted it as that, so it was fine. Perhaps there was no better way. But why do we even need to say %d, %u, and %s to differentiate between numbers and strings? So C, as I said before, C's printf function relied on the types being inferred from the format string, so it can know how to extract the arguments, whereas format fprintf doesn't need to do that, since it actually knows the types at compile time. So the format library implemented already what would go on to become standard format and standard print in C++20 and C++23, respectively. So standard format and standard print use Python-like format strings. That means it's no longer necessary to specify the type at all in the format string. Maybe I could convert all our log statements to use that instead. Fixing thousands of log statements by hand would be hard work. So you can probably guess what's coming. It occurred to me that a printf to standard print converter would be something that could be useful to many people. So I set out to write such a clang-tidy check, knowing that I could get it reviewed properly by the people who knew what it was supposed to do and gain confidence in it before trying to apply it to our code. So Clang's existing parse printf string class already knew how to parse printf format strings in order to generate those warnings. I thought maybe that code could be used to help with the conversion, and it could, so I didn't have to write all that. So how hard can it be? It's just replacing %something with a pair of curly brackets, isn't it? Well, it took me over 2 years, but I wasn't really working on it all the time, and review is quite slow. And I now know more than I ever thought I would about printf format strings. Here's a quiz, a few things I learned along the way. So, as I said before, printf format strings conflate the types with how to display them. C integer promotion rules mean that a char is actually passed as an int. So people can and do print them as integers. Standard print logically defaults to printing them as characters. So it needs to be explicitly told to print them as integers with the D format specifier. I also discovered that the %d here isn't the most correct way to format a character with printf, since at least C99. Does anyone know what the correct, well, it's not that this is incorrect, but what is the proper way of printfing a char? Since C99 anyway. No? Okay. Well, it's HH. Well, I think they consider, H is of course for short. So I think it's a short, as a, in comparison to a long, it's a shorter char. Something that's even shorter than short. So people have a habit of printing signed integers as unsigned and vice versa by using the wrong format specifier. And that works with printf. It might not always have been strictly portable. I think it now is with C++20 actually portable because it mandates that signed integers have to be 2's complement. But I'm not expert, don't believe me. A simplistic conversion to standard print generates different outputs since the signedness is now coming from the type rather than from the format string. So those outputs are different. It's not what we want. So if you want to ensure identical behavior after converting to standard print, then the check needs to insert casts. Yes. So you can see that there are two casts that are added where they needed to be, but not where they didn't need to be because the type matched. But this usually doesn't matter. So it's only enabled if the special strict mode is enabled in the configuration. The concept of strict mode is widespread in clang-tidy. There are times where it does. Often you don't want it to have to do the whole really strictly correct job because it does things like this and adds casts where really it's not necessary because most of the time people aren't actually they don't actually care about the sign of the thing they're printing. So, having implemented everything I could think of and writing lots of test cases, I sent the test cases off to the author of the format library and also the standards proposal for standard format for review. They were kind enough to do so, and they pointed out that I failed to spot the argument order changed when dealing with width and precision. So you can see there that printf and standard print disagree with the order of the arguments. And after looking at it and for a while, I realized, to quote Sean Parent, it's a rotate. So this turned out to be less than trivial to solve because those casts that I was adding and the ceasure removal all had to be done as well. So it's not actually a call to standard rotate. That may just be because I'm not algorithmically aware enough to turn it into a call to standard rotate. But I should probably have another go. Try and do it without a raw loop. So I managed to get the modernize-use-std-print clang-tidy check accepted into clang-tidy last year, and various improvements to it have landed since. By submitting it upstream, we got the benefit of wider review that the check is correct. I'm not going to show you the implementation in its entirety, but these are the files to look at if you're interested. So this is the bit that does the conversion of the format strings. This is the actual using standard print check, which is quite a lot smaller, that implements the check. And these are all the tests, the lit tests. The check provides configuration options to specify the functions to convert calls to, so that you can use it with format print too if you aren't on C++23 yet. And there's loads of documentation for it as well. So I've used some extra formatting options here to better show the stuff the check has to handle. I can't just replace the format strings and leave the call the same because the check will not be idempotent. Any statements in headers might be processed more than once. This isn't more than once in parallel because run clang-tidy sorts that out. It's more when you're building the multiple build configurations. It might be processed more than once. It's not really possible to tell whether the conversion has already been done. At a minimum, we just keep adding pairs of curly brackets all the time, which isn't really very useful. So the solution I had was to cheat, and I changed the check to replace the operator bracket function call operator with a uniquely named method call instead. I added that method call for testing, and then just used search and replace afterwards to get rid of it. Yeah, that was really easy to do because I could control the name and I knew I wouldn't conflict with anything else. A proper clang-tidy check would have been safer, but it was fine. There was some internal discussion within the team of whether we should land it like that with that new function call in and then do the rename afterwards as a separate change. That was popular because we could then land the changes gradually. We wouldn't have to do it all in one go. And so that seemed safer. But it was also unpopular because it would cause churn on lines that would ultimately put back to exactly how they were because they didn't contain any parameter substitution. So in the end, we decided to land it as a single commit. That way we could teach Git to ignore that change when blaming as well. So, and after the rename, we're left with the desired result. And as you can see, the second line in each of those functions didn't change. So that ended up with 5,000 more lines of change in about 440 files, but not the ones that didn't use a % or curly brackets or whatever in the format string, because they didn't need to change. So although I got all the underpinnings of this clang-tidy check to land as part of the modernize-use-std-print check, the check for our log classes was too specific to our use case, really. If you want to look at it, you can find it on GitHub there. But before I could land the results of the conversion, I had to investigate a strange crash that it caused during the unit tests. It involved an uncaught exception, calling fork, redirecting file descriptors, non-blocking file descriptors, signals, executing Node.js, and it was only reproducible under Valgrind. Oh, and the problem wasn't in the unit test code, it was in the actual production code. So luckily the problem was completely reproducible, but all those complexities made it rather hard to run under a debugger. And staring at it for a while didn't help. So I had lots of computer time at my disposal, so I decided to get the computer to narrow down the problem for me. I committed each file that the clang-tidy check had changed individually, since this was before the search and replace step. They were independent from each other. Then I used git bisect to identify the exact one of those changes that introduced the failure. I'm not going to describe how, there are loads of guides of how to use git bisect out there on the internet. Ultimately, the logging before running the check ended up calling the code in the top half, and after, it was the code in the bottom half. So the problem was due to format fprintf dealing with errors writing to the output stream by returning an error code like printf would have done, but format print and standard print threw an exception instead. But that's fine. We dealt with the exception, didn't we? We catch the exception. But then what do? We do use format print again. And if that one throws, then the exception leaks out. So the crash was basically due to that exception leaking out. So this commit each file and bisect technique may well be used for other large-scale changes. I'll certainly plan to use it again. We haven't had any problems on the embedded devices themselves yet. So right back at the beginning of this, when we were using C's fprintf, GTC and clang would check that the format string matched the parameters that were passed in. That was really important, since getting it wrong could cause undefined behavior, crashes, incorrect output. The switch to the format library meant we'd lost those compile time checks. But C++20 means we can get those checks back. We haven't done this yet because we're still on C++17, but it will be one of the first things we do once we upgrade the compiler. The error messages aren't great, but they're better than a runtime error. So our code for logging is quite simple, but there are definitely well-respected alternatives. Spdlog is a modern logging library based on the format library. Perhaps we should move away from our custom code to using it instead. We could insert it underneath our always log class if necessary. Alternatively, we could write a check to get clang-tidy to replace all the call sites and then remove all the static class instances. And of course, in C++20, we'd still get error messages for the format strings not being correct. We haven't decided to do this yet, but there are changes afoot in our logging, so maybe we will. So with all that fixed, I started looking for other uses of printf. I identified our long-serving helper function, strprintf, which does an sprintf to a string. I'm sure many of you have such a function, or have you in the past had such a function. I could convert these calls to standard format or format. But upstream wouldn't be interested in a, clang-tidy, they wouldn't be interested in a check for our own private function, even if lots of code bases have such a function. But I discovered the abseil library provides a version of this function. And clang-tidy contains lots of other abseil checks, possibly the Google link there. So I thought maybe I would be able to get a converter for this function upstream, and then I could just use it for our function. And after a little bit of pushback and a long wait, I did manage to. So clang-tidy now also has a modernize-use-std-print check. By following the same path as before of implementing a check that is generally useful, I could then adapt it for our use case. So this is the same format string converter as before. It just needed a few little minor changes. That's the new check to use standard format. It's similar to the use standard print one, but it's still quite small. And these are all the lit tests. So in this case for us, all I needed to do was configure the check to expect to change our function, and we were converting it to format because we still aren't using C++20. So with another 1,000 more files, 1,000 more lines changed across about 200 files, we've got to the 7,000 I promised. So although the new clang-tidy checks and our modifications work well enough for us, they aren't perfect. The checks as currently written expand all macros in the format string. This is good and exactly what we want when replacing the int types macros. But other uses of macros are more complicated. Perhaps we could fix cases where macros don't contain format specifiers, as long as we left the macro reference alone, because its value might differ between builds. Fixing general macros where the format specifier is behind a macro is hard and really very dangerous. But perhaps we could support providing a list of macros that are safe to expand to the check itself. So I have changes, which I haven't pushed for review yet, that only replace macros that come from the inttypes.h header. So I didn't want to push them for review and then have to deal with all the review comments whilst I was here. So another problem is in templated code. The calls we replaced here does not depend on the template parameters. But clang-tidy still doesn't seem to notice it. I've not investigated why and whether it would be possible to fix that, but that's on my list. Luckily, we haven't had too many of those. So it's 2024, so it's compulsory to talk about AI in every talk. Although I don't really use any machine learning stuff in my normal work, I did try it a few times for this. I found that ChatGPT was helpful to check that I hadn't missed an easier way to do something, and to point me at the right function names to look up in the documentation. It didn't do any real work for me, but it did save me research time. LLVM doesn't have an official policy, as far as I can tell, on the use of AI tools, but to be honest, given that it didn't write any code for me, I think it was fine. I asked it things like, how can I tell if the function decal includes a variable argument list? In this context, how can I tell the difference between a C-style variadic function, that's another one for the bingo card, and a template variadic function? Please write a function to go into LLVM that converts a type to its unsigned counterpart. The main reason I asked that one was to find out if there was already a function in LLVM that just did that. And when it proceeded to spew out a load of code, I went, oh, well, there isn't then. I think the code it came up with was mostly okay, but not quite right. I had to write it myself. So I'd like to say thank you to everyone on this list who reviewed these new clang-tidy checks. So hopefully my experience will inspire you to make use of these clang-tidy checks and perhaps adapt them when you need to. Compiling clang-tidy takes a lot of CPU time, but it's not difficult to do. I'm no C++ language lawyer and parsing expert. I stared at the abstract syntax tree dump of example code, trying to work out what to match on. If you write a general purpose check, then you can get it reviewed and improve it before configuring it or customizing it slightly for your use case. I couldn't find it. When I was writing this presentation, I couldn't get the ordering to work right. So that's the readability remove Seastra check. I implemented that for standard format and standard print. And that was all reviewed and landed right back at the beginning of this process. The great thing there was the reviewer told me how to make it handle multiple arguments. The one I'd implemented would only fix the first argument. So you need to keep running the same check over and over again as it worked its way, fixing the arguments. So you're probably only going to be fixing your code once. So it doesn't matter if your clang-tidy modifications are a bit hacky and don't really make it upstream. And sometimes falling back to search and replace can be quicker and easier when that's all that's required. There are really good guides for getting started with this stuff. You can look at other similar checks to find ways to do things. You can browse through, there's a great long list of the AST matches. And I often found, once I got the code to compile, it did something close to what I wanted. The DSL is really quite good. Upstream reviewers are very helpful, but they can be slow, and it sometimes took me quite a while to understand what their comments were telling me to do. I'm not an LLVM committer. I needed to get the reviewers to land my changes for me, and don't be put off by how long it took me. I'm sure someone more persistent and focused would have been quicker. So it's been a pleasure to present my first ever conference talk to you all. I hope I've shown you that making use of clang-tidy and even modifying it is easier than you might have thought and given you some ideas. Thank you.